Calculate the ideal mechanical advantage of a lever in which the effort arm is this much and load arm is this much. So if we consider the lever as ideal, then the mechanical advantage will be equal to the velocity ratio. And velocity ratio is related to effort arm divided by load arm. So this formula you should know. This formula we should be knowing. Then we'll just put these values and we'll get the answer as 15. Draw a diagram to illustrate the action of bicep muscles as a lever. Name the class of the lever. So this is the class 3 lever. Why? Because if you see, I will point out. So this point, let me put it with the red point. So this is our fulcrum. It is little behind where actually the effort is pulled up. So the effort is going in this direction. So this is effort. So we want to say point. This will the effort point pulling upwards. And here it is the load which we are picking up. We use another color for this. So this is the load. Okay, in this case, the load will be lesser than the effort. We will put a lot of effort, but only the lesser, load can be picked up. So if you see in between what it is, in between there is an effort, and these kind of levers are called class 3 levers. So it will be class 3, and you can show it by diagram. So there is one connected question here. In class 3, mechanical advantage is always less than 1. Why? Or you can say the if you're thinking about ideal case, then why velocity ratio is always less than 1. So it is very simple. You have to just focus on this formula. If m is equal to vr, vr has this formula, effort arm divided by load arm. So in case of class 3, what will happen? The effort will go in between. So if you see the length of effort arm will be this much, and the load arm will be always bigger than the effort arm. So the load arm is always bigger. So this value goes high and this value is small. So obviously you will get to this fraction. The answer will be always less than 1. That's why we say for class 3 lever, the MA is always less than 1. Let's go next. A machine is driven by a 100 kg mass that falls 8 meters in 4 seconds. It lifts a load of mass 500 kg vertically upwards. Taking G is equal to this much. Calculate the force exerted by the falling mass. Okay. B, the work done by the falling mass and its displacement, 8 meter. The power input to the machine, the power input has been asked. The power output of the machine if the efficiency is 60%. And then the work done by the machine, or you can say work output. So let us do attend this question step by step. First thing, force exerted by mass. So mass is given of 100 kg. See, the mass is given of 100 kg. So we just need to multiply by g. Mg is the force exerted or the weight. So this will be the g. We have to take 10. So we will do that and we will get 1000 Newton. So this is the force. Now this force, this mass will work on it. Gravity will work on this mass for 8 meters, right? So there'll be work done. So that 8 meters work can be calculated. Just multiply what is the force. So here is mg combined like 1000, which we just calculated. And we are just multiplying it by distance. As the mass falling like this, okay, the gravitational force is also in this direction and the 8 meter displacement is also in this direction. That is why the value of cos theta I have taken in here 1. So we will get 8000 joules as the answer. So this much work is done. Now they are asking in the third part is the power input to the machine. So this much work is done on the mass which is falling. Okay, and this mass is falling in 4 seconds. So we need to get power. Power is always per second basis. So we'll apply that formula. So 8,000 joules of work is being done and in 4 seconds. So we will just divide it by that. So then we will get 2000 watts. 2000 joules per second, and that's what the shorthand is, 2000 watts, and in SI we represent power as. So we'll write 2000 watts. So this is the power input. This is the power which machine is getting. But whether that machine is able to convert that work, convert that input to the output, that is the question. That is why the next part of the question starts. We need to calculate the power output of the machine if its efficiency is 60%. If it is 100%, what will happen? Entire 2000 watts, the output will also be 2000 watts. But now the efficiency is only 60% or zero point 0.6 if you think about in terms. So think about 60% as 0.6. So 0.6 times of the input only will be converted in power output. So you can follow the formula also of the efficiency if you want, like efficiency is equal to power output by power input and then come like this, or you can come by common sense, like the whatever the input we got, right? The input was 2000 watt. This is the efficiency. So that is what if we multiply this, 60% of this is only getting converted into the power output. So we will get, by intuition also we can reach to this conclusion. So 1200 watt. So the input was coming 1200, but output is only 1200. So where the rest went, that got dissipated. The friction forces are there. There is air friction. There are machinery has some instruments, they also take some energy, like that there are multiple energies of sound energy can dissipate the energy, so there is a loss because it is a practical machine they are talking about. Okay, let's go for the E option, the work done by the machine in 4 seconds. Now they are asking here, note it down, by the machine, so they are talking about the output. So we have got the output power. What does that mean? 1200 joules of work is done in 1 second. So what, always remember what is joules per second. So that makes us, the units of what doesn't make much, understanding. If you know what stands for joules per second, that gives us more intuition, like 12,000 joules, 1200 joules of work is done in 1 second. They are asking the work done by the machine in 4 seconds. So we will just multiply it by 4 and we will get as 4,800 joules. So that will be our answer. Let's go to the next example. A crowbar 2 meter long is pivoted about a point 10 centimeter from its tip. Calculate the mechanical advantage of the crowbar. What is the least force which must be applied at the other end to displace a load of 10 kgf? So first let's calculate its mechanical advantage. So this is the crowbar I have taken. It is total length is 2 meter, because they have told we have a cross section here at 10 centimeter. I have converted into meter, zero point 0.1 meter. So the rest of the length will be 1.9, right? So this is the actually crowbar. So I'm just taking for simplicity, just a simple rod, which is getting pivoted. So here is a small pivot you can imagine, which we are pivoting from here, and we are picking up load with it. Now, how we can solve this? See, they are asking about mechanical advantage. If we assume that this is an ideal scenario, then we can calculate the VR, right? VR, and it will be equal to mechanical advantage, and that is effort arm divided by load arm. So effort arm is this much, 1.9. We have to divide it by load arm, that is this much, usually zero point 0.1. So 1.9 divided by zero point 0.1 is equal to 19. Now we have considered as ideal machine assumed, then the answer will be of 19. So what we are doing, what we can understand, so it is MA, what we can understand with this 19 number, that 19 times force you can generate from here. By the way, this kind of a lever will be called class 1 lever. They did not ask because fulcrum is in between. Okay, let's go ahead. Now let's do the next part, which is asking what is the least force which must be applied at the other end to displace a load of 100 kgf. So assuming there is no other losses, we can just apply 1 by 19th of the load. So if 100 load is there, we just have to provide 1 by 19th force, because mechanical advantages of 19 and that R force will become 19 times. So what will be able to pull? We will be able to pull 100 here. So this way, by intuition, you can guess it, like from mechanical advantage, how much force we need to apply. Because 19 is the mechanical advantage, we just have to apply 1 by 19th of the force. So that's why we'll do just 100 kgf into 1 by 19, and we will solve this. You can solve it like this also if you want to divide, and you will get 5.26 kilogram force that you need to apply. Okay, so many less. Actually, if you see that 20 times less force we need to apply, right? Around. Okay, let's go to the next question. A uniform seesaw, 5-meter long, is supported at its center. A boy weighing 40 kilogram force sits at a distance of 1 meter from the center of the seesaw. Okay, to which class of lever does it belong? Find where the girl of weight 20 kilogram force must sit on the other side of the seesaw so as to balance the weight of the boy. So first thing is it is fulcrum in between. Whenever the fulcrum is in between, we say it is the first class. If load is in between, we say second class. If effort is in between, we say third class. So that's how we remember this. Now what they are asking is, two person need to be sit, and they are asking where to make them sit. So we can treat this problem as a principle of movement problem. By intuition also you can calculate this. For example, let's say, so this guy is 40 kg. Okay, the other person which we want to sit is just half of the force it will apply, 20. So the reverse action will happen to the distance. So if we are decreasing the force, right, the distance will be doubled. So that will be of 2 meter, right? 40 is getting into 20, it is getting half. So distance will be doubled, 1 meter to 2 meter to other side to balance. So it's a simple problem of principle of movement, but we can apply it here also, principle of movement, if you see. So this is 1 meter distance that 40 kgf boy sits here. So it will be acting downwards. And now we don't know how where to make this person sit. Let's say X distance or D distance. So to balance, anti-clockwise and clockwise movements must cancel. So we will do this magnitude 20 kgf X will be equal to 40 kgf into 1. And then we will arrive at this answer, which we were able to calculate by intuition also. Okay, let's go next question. A cook uses a fire tongue of length 28 centimeter to lift a piece of burning coal of mass 250 gram. So the load we need to pick is a 250 gram force. If he applies the effort at a distance of 7 centimeter from the fulcrum, find the effort. Take G is equal to 10. Okay, so this is the fire tongue. Okay, to pick up the hot objects, we can use it to burn, like burning coal. So let's say this is the burning coal. So we can apply the effort here so that it helps us to keep a distance from the hot object. So it is given that the effort is at a distance of 7 centimeter. Note it down here. So the length of tongue length is 28 centimeter. So load is getting picked here, 28 centimeter. Now we just need to apply formulas. Let's say we have VR effort arm divided by load arm. So effort arm, if you see, it is 7. Load arm is 28, so it will be 7 by 28 or 1 by 4. So here the 1 by 4 is the velocity ratio. If the lever is ideal, mostly we can assume, so it will be VR is equal to MA. So mechanical advantages of 1/4. See, here the mechanical advantage is not greater than 1. This is our type 3 lever. Okay, this is the type 3 lever I have noted down here. And in that, always we will get mechanical advantage less. Okay, so you have to apply lot of load here, effort here to get very less load. Okay, so you will be able to pick very less. So force is getting decreased actually. It is getting 1/4 this time, right? It is not a force multiplier, but it is reducing our effort actually. So now what to do? See, what we want to do, we want to have this much of force. And our force, we know from mechanical advantages of 1 by 4. So our force will get 1/4 to get this. So we will apply effort 4 times to this so that when it got reduces 1 by 4, we get this much of load we'll be able to pick. So that way we can pick the intuition that the answer will be 4 multiplied by 250 gram force. But mathematically, let us see how we can arrive at the same conclusion. So we are assuming this ideal lever VR is equal to MA. MA we know load divided by effort. We want to know the effort. So load divided by MA 250 1 by 4. Now you see that 4 will go up, right? It is a fraction. 1 by 4. So 1 will remain here and 4 will go up. So it will get multiplied. That is what the intuition we were trying to build upon. So this will be 1000 gram force, or we can change it to kilogram force. And we have to multiply by 10 to the power minus 3. And then we can multiply it into 10. Why? Because G's value is given as 10 to be taken. If you want to convert kilogram force into newtons, so that also we can do. So the answer will be of 10 Newton. Okay, let's go next question. The diagram below shows a lever in use. To which class of lever does it belong? Give one example of this class. So there are many examples of this class. This is a typical class 1 lever. Scissors as one example where the fulcrum is between. So whenever you are trying to find the type of this one, we have to just see which class by finding out what is in between. So fulcrum is in between, it is a first class. Now what they are asking else, they have given this distances. I made this diagram. Now we need to calculate. Yeah, the options I have written it here. So first thing is it belongs to class 1 as fulcrum is in between. Seesaw is also one example. Now the B option is how will the mechanical advantage of lever change if load is shifted towards the fulcrum without changing its dimension. See, the load is getting shifted. So what we are doing is we are instead of 0.2 meter, we are putting it somewhere here. So what they are asking is what will happen to our mechanical advantage? Will it increase or decrease? Our mechanical advantage will increase. Why? Just see what VR is. You know, VR is an ideally is equal to mechanical advantage. So it is effort arm divided by load arm, right? So you are decreasing this part. So if you are decreasing this part, then what will happen? The VR value will increase or the mechanical advantage will increase, right? So if we decrease the denominator, the VL will increase or MA will increase. We can say because we are assuming that this is ideal situation, MA is equal to VR. Okay, so let's go. Next part of this question is we have to calculate the mechanical advantage of this. So mechanical advantage of this will be uh, we have to calculate by VR we can calculate. So whatever the value of MA will come, that will be equal to VR. So MA is equal to VR by effort arm by load arm. See, effort arm will be, where is effort? Effort is this much. So 2 minus 1.8. So it'll be 1.8 and the load arm is this. So it'll be 1 point, 1.8 divided by 0.2. We can get mechanical advantage of 9. Now, hence mechanical advantage MA is equal to 9. So we need to apply 180 kg of now. If the mechanical advantages of 9, what intuition we can take it from here, that we just need to pick up the weight, we just need to apply 1/9 of that force. So we need to apply 180, we need to pull up, so we just need to apply 1/9 of effort, right? 1/9 into this, or we can say 20 kgf only we need to apply here. This 18 kgf, 20 kgf only we need. 18 kgf it is, sorry, it's not 180, sorry, so it is not 180, so it will be 2 kgf will be the answer. But we got the answer. Like we can, when we know the mechanical advantage from there, we can easily by intuition guess how much effort we need to put. If the mechanical advantages in this case was 2, so how much I need to apply the force, whatever you want to pick, just half it. If it is 3, whatever weight you want to pick, just third of that you need to apply. Here it was 9, to 1/9 of that weight which you want to pick, we are applying here, and we'll be able to pick it up. Okay, let's go example 8. A nut which can be opened by applying a force of 40 kgf is broken by using a nut cracker having its handle 20 centimeter long by placing it at a distance 2 centimeter from the hinge. Calculate the minimum force needed to break the nut. So what is the minimum force is needed to break the nut effort, actually the minimum effort which we need to apply. So this is a diagram of a nut cracker. We keep the nut in between and we apply effort from here. Okay, so we apply less effort and we get more, more force here. It is a force multiplier. So nutcracker is, first thing is, it is a class 2 lever. Now assuming ideal machine MA will be equal to VR, whatever mechanical advantage we'll get, that will be equal to VR. VR is effort arm by load arm. See the effort arm here till here, it is 20 centimeter, and the load arm is 2 centimeter. So it will be 20 centimeter divided by 2 centimeter, that will be 10. So we got the mechanical advantage of 10. What does that mean? If you want to apply this much force, just apply, want to get this much force, you just have to apply 1/10 of that force to get this. So 40 1/10 will be 4 kgf. So we have to only apply 4 kgf of force to get this much of force to crack, which is will be sufficient to crack the nut open. Okay, let's go next. Example 9. A man can open a nut by applying a force of 150 Newton by using a lever handle of 0.4 meter. What should be the length of the handle if he's able to open it by applying a force of 60 Newton? Now what he's doing is decreasing the force. So the distance will increase, but how much? Let's check mathematically. And this question is like mostly we can solve it by moment of force better. So what we can do, torque produces 150 into 0.4. 150 was applying force. With the distance of this, we can calculate the magnitude of moment of force or torque. Now we want same torque to be produced, but by with this force. So we'll just see, okay, this much should be equal to 60 into this length, which will be this length that we not want to calculate. We solve for this L and we will get it as 1 meter. So we need a longer lever if you want to reduce the force. 150 by 60 you're reducing force, so we have to compensate by increasing the distance of the lever.